Imagine a place in space where nothing, not even light, can escape. A place where time itself is twisted and distorted. This is the reality of black holes, a phenomenon so strange that they challenge our understanding of the universe. But what if I told you that black holes might not be the only mind-bending objects in space? Enter wormholes, theoretical passages that could connect distant regions of the universe, or even different universes altogether. The existence of black holes and wormholes has fascinated scientists and the public alike for decades. These objects are not just science fiction, they are rooted in the most sophisticated theories of physics. But what exactly are they? Why do they hold such fascination, and how do they challenge the limits of human knowledge? Black holes were first predicted by Albert Einstein's theory of general relativity in 1915, but it wasn't until the 1970s that physicists started to fully understand their potential. The concept of a wormhole, on the other hand, was born out of the same equations, but it remained a theoretical idea, with no direct evidence to support it. Despite their mysterious nature, black holes and wormholes share a deep connection. Both are consequences of the warping of spacetime, a fundamental feature of the universe. In this section, we will explore black holes in detail, how they form, how they behave, and how scientists are attempting to study them. Then, we will transition into the world of wormholes and how they might one day unlock secrets of space travel and time manipulation. What is a black hole? At the most basic level, a black hole is a region in space where the gravitational pull is so strong that not even light can escape. The idea of something so dense and massive that it could trap light might sound impossible, but black holes are very real. They form when a massive star collapses under its own gravity at the end of its life. The core of the star implodes, creating a singularity, a point of infinite density. Around this singularity, the space is warped to such an extent that nothing that crosses its boundary, known as the event horizon, can escape. The event horizon acts like a one-way gate. Once something crosses it, it is doomed to be pulled inward forever. Black holes come in different sizes. Stellar black holes form from the collapse of massive stars and typically have a mass between 3 and 10 times that of the Sun. Supermassive black holes, on the other hand, are found at the centers of most galaxies, including our own Milky Way, and have masses that range from millions to billions of times that of the Sun. The supermassive black hole at the heart of the Milky Way, named Sagittarius A*, has a mass of about 4 million solar masses. Despite their name, black holes are not actually holes in the traditional sense. They are incredibly dense objects, with an immense amount of mass packed into a tiny region. This dense mass causes spacetime to bend so sharply that it creates a gravitational well, from which nothing can escape. The key feature of black holes that captures the imagination of scientists and laypeople alike is their event horizon. This boundary marks the point at which the escape velocity, the speed needed to break free from the black hole's gravity, becomes greater than the speed of light. Once you cross this boundary, you can no longer observe or interact with the black hole from the outside. Anything inside the event horizon is lost to the black hole forever, making them a one-way ticket to an unknown fate. The types of black holes. There are 3 main types of black holes: stellar black holes, supermassive black holes, and intermediate black holes. As we mentioned, stellar black holes form from the collapse of large stars. These are the most common type of black hole, and they range in mass from about 3 to 10 solar masses. They are often found in binary systems, where 2 stars orbit each other. When one of these stars runs out of fuel and collapses, it can create a black hole. If the companion star is close enough, matter from the companion can be pulled toward the black hole, forming an accretion disk. The matter in the accretion disk heats up due to friction and radiation, emitting powerful X-rays and other radiation that can be detected by telescopes. Supermassive black holes, as their name suggests, are much larger than stellar black holes. They reside at the centers of most galaxies, including our own Milky Way. These black holes can have masses ranging from millions to billions of solar masses, and their formation remains one of the great mysteries in astrophysics. Some scientists believe that supermassive black holes could have formed during the early stages of the universe, when large amounts of gas and dust coalesced to form a singularity. Others propose that they could have grown over time by merging with other black holes or by accreting matter from their surroundings. Intermediate black holes are a more elusive class of black holes. They are thought to have masses between 100 and 1,000 solar masses. While their existence has been theorized, evidence for them has only recently started to emerge. Intermediate black holes could provide important clues about the formation of supermassive black holes and the evolution of galaxies. How do we detect black holes? Because black holes do not emit light, they are difficult to detect directly. However, scientists have developed several techniques to study them. One of the most common methods is to observe the behavior of nearby stars. When a black hole is part of a binary system, the gravitational pull from the black hole can cause the companion star to move in a way that reveals the presence of the invisible object. By measuring the star's orbit and the amount of light it emits, scientists can determine the mass and size of the black hole. Another method for detecting black holes is through the observation of X-rays and other forms of radiation emitted by the accretion disk. As matter falls into a black hole, it gets compressed and heated to incredibly high temperatures, emitting radiation that can be detected by space telescopes. These observations can help scientists infer the properties of the black hole, such as its mass, spin, and the size of its event horizon. Gravitational waves, which are ripples in spacetime caused by the acceleration of massive objects, provide another way to detect black holes. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, made the groundbreaking discovery of gravitational waves from a black hole merger. This discovery confirmed a major prediction of Einstein's theory of general relativity and opened up a new era of black hole research. As we continue to improve our observational techniques, scientists hope to learn more about the properties of black holes, including how they might behave at the quantum level. This knowledge could have profound implications for our understanding of gravity, space, and time itself. In the next section, we will explore the fascinating possibility of wormholes and how they could potentially allow us to travel across vast distances in the universe, or even between different universes. Theoretical passages, wormholes and their fascinating possibilities. Wormholes are one of the most mind-bending and mysterious concepts in modern physics. They offer the tantalizing possibility of shortcuts through space and time, allowing us to travel vast distances in the universe almost instantaneously. Imagine stepping into a wormhole and emerging on the other side of the universe, or even in an entirely different universe. It sounds like science fiction, but wormholes are a direct consequence of the equations of general relativity, just like black holes. However, unlike black holes, which have been observed in nature, wormholes remain a purely theoretical concept, at least for now. In this section, we'll explore the theory behind wormholes, how they might work, and what challenges they present to our understanding of the universe. What is a wormhole? A wormhole, also known as an Einstein-Rosen bridge, is a hypothetical tunnel-like structure in spacetime that could connect two distant points in the universe, or even separate regions of spacetime entirely. The concept of a wormhole originates from the field of general relativity, which describes how massive objects like stars and black holes distort the fabric of spacetime. In theory, a wormhole forms when spacetime is bent so sharply that two distant points are connected by a bridge. This bridge could allow for instantaneous travel between the 2 points, bypassing the vast distances between them. Wormholes are often depicted as tunnels with 2 ends, each located in different parts of space and time. These tunnels could theoretically allow for faster-than-light travel, something that is not possible using conventional means. If wormholes do exist, they could provide an entirely new way to explore the universe, one that would make traveling across the cosmos a much more feasible task. However, despite their theoretical underpinnings, wormholes remain speculative objects with no experimental evidence to support their existence. The first mathematical model of a wormhole was proposed in 1935 by physicists Albert Einstein and Nathan Rosen. They derived the solution to Einstein's equations of general relativity and found that it described a tunnel-like structure connecting two separate regions of spacetime. This solution, known as the Einstein-Rosen bridge, was initially seen as an interesting mathematical curiosity rather than a physically realistic object. However, in the decades that followed, physicists began to explore the possibility that wormholes could exist in the real universe. How do wormholes work? At a basic level, a wormhole is a shortcut through spacetime. To understand how it might work, it helps to think of spacetime as a two-dimensional surface. If you were to fold this surface so that two distant points touch, you could create a direct path between them. This is similar to how a wormhole could connect two distant regions of the universe, bending spacetime in such a way that traveling through the wormhole would be much faster than traveling through normal space. In order to create a traversable wormhole, one that could allow for human travel, several conditions would need to be met. First, the wormhole would need to remain stable. Without some form of support, wormholes are theorized to collapse almost instantaneously upon being formed. This is where the concept of exotic matter comes into play. Exotic matter refers to hypothetical substances that have negative energy and could, in theory, hold open the mouth of a wormhole long enough for something to pass through. Exotic matter is very different from ordinary matter, which has positive energy and causes spacetime to curve in a normal way. Exotic matter would have the opposite effect, counteracting the gravitational forces that would otherwise cause the wormhole to collapse. The idea of exotic matter is still highly speculative, and no known particles or substances exhibit the required properties. However, theoretical physicists are still exploring the possibility that exotic matter could exist in some form, perhaps in the quantum realm. Until such exotic matter is discovered, wormholes remain firmly in the realm of speculation. Types of wormholes. There are several different types of wormholes, each with its own theoretical characteristics. The most commonly discussed are traversable wormholes and non-traversable wormholes. 1. Traversable wormholes. Traversable wormholes are the type of wormhole that would allow for the passage of matter, such as humans or spaceships. These wormholes would need to be stable and large enough to accommodate a person or spacecraft. The theoretical model of a traversable wormhole requires exotic matter to keep it open, as mentioned earlier. If such a wormhole could be created, it could serve as a shortcut between two distant points in space and time. 2. Non-traversable wormholes. Non-traversable wormholes, also known as Einstein-Rosen bridges, are the original concept of wormholes proposed by Einstein and Rosen. These wormholes connect two regions of spacetime but are not stable enough for anything to pass through. Any matter that enters a non-traversable wormhole would be crushed by the immense gravitational forces at the singularity, making it impossible for anything to survive the journey. These wormholes are theoretical objects, but they still play an important role in our understanding of the nature of spacetime. 3. Wormholes as time machines. One of the most intriguing aspects of wormholes is their potential to allow for time travel. In theory, if a wormhole could connect two regions of spacetime that are separated not just by distance but also by time, it could allow for travel into the past or future. This idea has been explored in numerous science fiction stories, but it is also taken seriously by some physicists. The key to this concept lies in the possibility that a wormhole could be connected to different points in time, not just space. However, the idea of using wormholes for time travel presents some serious paradoxes. For example, if someone were to travel back in time through a wormhole and alter events in the past, this could lead to a contradiction, what is known as a grandfather paradox. In this scenario, a traveler could potentially prevent their own existence, creating a logical conundrum. Some scientists believe that the universe might have built-in protections to prevent such paradoxes, while others argue that time travel through wormholes might be inherently impossible. Challenges of wormhole travel. While the idea of wormholes is fascinating, there are numerous challenges that must be overcome before they can be considered a viable means of travel. The most significant challenge is the need for exotic matter, as mentioned earlier. Without exotic matter to keep a wormhole open, it is thought that the wormhole would collapse before anything could pass through. Even if exotic matter were discovered, it would likely be incredibly difficult to manipulate and control. Another challenge is the immense energy requirements that would be needed to create and stabilize a wormhole. Theoretical calculations suggest that the energy required to create a traversable wormhole could be on the order of the total energy output of an entire galaxy. This makes wormhole travel seem, at least for the time being, like an impossibility. Despite these challenges, the idea of wormholes continues to inspire scientists and science fiction writers alike. Theoretical physicists like Kip Thorne and others have explored the possibility of wormhole travel in depth, and while we are far from being able to build or travel through a wormhole, the concept remains a fascinating and important area of research. The future of black holes and wormholes, what lies beyond? As we wrap up our journey through the enigmatic realms of black holes and wormholes, it's essential to reflect on the profound implications these cosmic phenomena have for our understanding of the universe. What have we learned so far? Black holes, with their impenetrable event horizons and infinite density, are some of the most awe-inspiring objects in the cosmos. They challenge our understanding of gravity, time, and space itself. Wormholes, though still theoretical, hold the tantalizing possibility of revolutionizing space travel and even our concept of time. The question now becomes, what does the future hold for black holes and wormholes? Are they the keys to unlocking the mysteries of the universe, or will they remain elusive concepts, forever out of reach? Black holes and the quest for knowledge. The study of black holes has already led to some of the most groundbreaking discoveries in physics. In 2015, the detection of gravitational waves from the collision of two black holes confirmed a major prediction of Einstein's general theory of relativity. This discovery not only validated decades of theoretical work but also opened a new window into the universe. Gravitational waves are ripples in spacetime caused by massive objects accelerating through space, and their detection allows scientists to study cosmic events that were previously invisible. In recent years, the Event Horizon Telescope, EHT, made history by capturing the first-ever image of a black hole, the supermassive black hole at the center of the galaxy M87. This image, released in 2019, was a major milestone in black hole research. It provided direct visual evidence of the existence of black holes and allowed scientists to begin testing some of the most extreme predictions of general relativity. The study of black holes also holds profound implications for the future of physics. One of the biggest mysteries surrounding black holes is the information paradox. According to quantum mechanics, information about the state of a system cannot be lost, but when something falls into a black hole, it seems to disappear beyond the event horizon. This contradiction between quantum mechanics and general relativity has led to ongoing debates among physicists. Some propose that the information may be preserved in a quantum foam at the black hole's event horizon, while others suggest that the information could be stored in a holographic form, a concept known as the holographic principle. Future advancements in technology and observational methods will continue to push the boundaries of black hole research. Instruments like the Laser Interferometer Space Antenna, LISA, a space-based observatory designed to detect gravitational waves, will likely provide even more insights into black hole mergers and other cosmic events. As we develop more advanced telescopes and observation techniques, we will continue to test the limits of our understanding and hopefully unlock some of the deepest secrets of the universe. Wormholes, a glimpse into the future. As for wormholes, their potential for revolutionizing our understanding of space and time is unparalleled. If wormholes can indeed be stabilized and made traversable, they could allow for instantaneous travel across the cosmos, or even between different universes. This would completely transform our understanding of space travel and possibly allow us to explore distant stars, galaxies, and even parallel realities. However, for all the excitement surrounding wormholes, there are many obstacles that must be overcome. As we discussed earlier, the biggest hurdle is the need for exotic matter to keep a wormhole open. This exotic matter, with its negative energy, could provide the necessary support to prevent the wormhole from collapsing under its own gravity. But we are still far from discovering or creating this exotic matter in any practical form. Even if exotic matter were to be discovered, there would still be immense technological challenges involved in manipulating and controlling it. Creating and stabilizing a wormhole would likely require an unprecedented amount of energy, far beyond anything we are currently capable of producing. And while the theoretical possibility of wormhole travel is exciting, it is important to remember that we are still in the realm of speculation. Many physicists remain skeptical about the practicality of wormholes, given the numerous theoretical and engineering challenges involved. That being said, the exploration of wormholes is far from over. Theoretical physicists are still working on ways to make wormholes more than just mathematical curiosities. Some researchers are investigating the possibility that wormholes could exist in higher dimensions, dimensions beyond the familiar three spatial dimensions and one-time dimension that we experience. If this is the case, it could open up entirely new possibilities for interdimensional travel and exploration. Moreover, the study of wormholes could have important implications for other areas of physics, including quantum mechanics and the nature of gravity. The idea that wormholes could connect different regions of spacetime, perhaps even different universes, challenges our basic assumptions about the structure of reality itself. If wormholes are ever proven to exist, they could fundamentally change our understanding of the cosmos and our place within it. The broader implications of black holes and wormholes. Beyond their potential for scientific discovery and space exploration, black holes and wormholes also raise profound philosophical questions about the nature of the universe. Black holes, for instance, challenge our concept of space and time. What happens to time inside a black hole? According to general relativity, time slows down as you approach the event horizon, and at the singularity, time effectively comes to a stop. But quantum mechanics, which governs the behavior of particles on the smallest scales, suggests that time may behave very differently at the quantum level. This paradox is one of the central problems that physicists are trying to resolve, and it could have far-reaching implications for our understanding of the universe. Wormholes, on the other hand, push the boundaries of space and time even further. The possibility that they could allow for time travel or interdimensional travel raises questions about causality, free will, and the nature of reality itself. If we could travel through a wormhole to the past, would we be able to change the course of history? And if we could travel to another universe, what would we find? These are questions that have fascinated philosophers, scientists, and writers for centuries. The exploration of black holes and wormholes is not just about understanding the mechanics of the universe, it is about questioning our place in it. What are the limits of human knowledge, and how far can we push those limits? As we continue to study these cosmic phenomena, we may uncover answers that challenge our most fundamental beliefs about the nature of reality. Whether black holes and wormholes lead to practical applications or remain theoretical concepts, they will continue to captivate our imagination and inspire the quest for knowledge. Final thoughts. The study of black holes and wormholes has taken us on an extraordinary journey into the heart of the universe. These cosmic phenomena challenge our understanding of space, time, and gravity, and they inspire us to push the boundaries of what we know. While there is still much we don't understand about black holes and wormholes, the progress we've made so far is a testament to the power of human curiosity and ingenuity. As we continue to explore these enigmatic objects, we will undoubtedly uncover new insights into the fabric of the universe. So, the next time you gaze up at the stars, remember that the universe is full of mysteries waiting to be discovered, and perhaps, one day, we will unlock the secrets of black holes and wormholes, taking us to the farthest reaches of the cosmos.